And so I'm going to go over one more example here of directly applying this theorem. And this has to do with a more complicated example, but also more relevant example towards applications. The previous two problems have been just examples to sort of illustrate where we're going and how we use the theorem. What we're going to consider now is the generalized predator-prey model that we talked about a number of weeks ago in our active learning sessions. So this is specifically the non-dimensionalized generalized predator-prey problem. This is found in the Ends book. This is one of our course texts. So you remember that this was the prey equation for x was a logistic type growth with a predation term that's saturated and the predator growth also depends on the relative ratio of predators to prey. This is equation 1 and equation 2. And it's a little bit more convenient to put these in a slightly nicer form for analysis. Simply by bringing them to common denominator and realizing that this first equation is the same thing as 1 minus x times x plus c minus axy divided by x plus c and y prime becomes b times y times x minus y over x is equal to 0. The equilibrium points of this system are a little bit more cumbersome to evaluate. We'll start with equation 2. Oops, and this should not equal 0 in general. When we set equation 2 equal to 0, we have two possible ways of satisfying this. Y can be equal to 0, or y can be equal to x. And in the case that y is equal to 0, we can satisfy equation 1 being equal to 0 by having x be equal to 1 or x be equal to negative c. which gives us the equilibrium point 1, 0, and the equilibrium point negative C0. For the y equals x term, we have a little bit more work. So if y equals x, this numerator is 0, therefore this equation is 0. But then this right here has to be 0 in order to satisfy equation 1. Which means that 1 minus x times x plus c minus axy which is just ax squared left equal to 0 because y is equal to x. And this expression will, oops, I just realized I need to have an x term right here. X term I wrote outside here, but that should be right here. Multiplied by this guy. It's important to point out too that x equals 0 is not a possible solution to this. Even though you can factor an x out here, x equals 0 is not a possible solution because of the division by 0 here. And this reduces to y being equal to 0 as well. So this is nice actually because we can factor this entire thing as x times 1 minus x times x plus c minus ax and if we go through, this becomes a quadratic formula for x that solves this term right here being equal to 0. And the exact expression you get is 1 minus c minus a plus or minus the square root of 1 minus c minus a squared plus 4c over 2 are the roots of this equation right here, which satisfy the equilibrium point conditions for equation 1 and equation 2, and therefore we have two new critical points, or equilibrium points. The equilibrium point x1, x1, and the equilibrium point x2, x2. x1 is the negative part of the square root, and x2 is the positive version of the square root. So we have 4 total equilibrium points, each one of which can be classified, but we're going to focus on equilibrium point x2, x2, because this is the equilibrium point that we're interested in the predator-prey model, where the populations are both positive. This equilibrium point lies in the first quadrant. We can get a nice picture of this just by looking at Desmos plot of the null lines along with the equilibrium points plotted on for any number of values. So let's open that up, take a look at that right now. And this is the Desmos plot of the null lines, where I've also included all of the equilibrium points that we solve for in terms of any general A, B, or C in the problem. And you can see that as we change any one of these values, the equilibrium points in general are going to change. But they change in a way that's predictable. We just solve for the exact values in terms of the parameters for the problems, so we know what each of these are going to be. It's also important to point out that when x is equal to negative c, we have a discontinuity. The same thing when x is equal to 0 here in the function itself. So we have a switching point in the sign of x prime and y prime at both of these. And this can be visualized just by looking at the region where x prime is positive. In this case, the red region right here and the blue region right here is the region where x prime is negative. Likewise, we do the same thing for y prime as well. But this will be important a little bit later on. So if we take our system and linearize it, specifically we look at the Jacobian matrix at our equilibrium point, our system is I prime is equal to this vector function of our variables, so the Jacobian matrix, as we take the derivatives, all the partial derivatives of g becomes the following: 1 minus ay over x plus c plus ay over x plus c squared minus 2 times x and then the y partial derivative of this will be ax over x plus c and the x partial derivative of this becomes b times y squared over x squared, and y partial derivative of this becomes b minus 2by over x. And so at the equilibrium point that we're interested in is x2, x2, we solved for before. The stability of this critical point will be determined by A, where A is the Jacobian matrix of G at psi star. And and this simplifies a little bit. The first term becomes 1 minus ax2 over x2 plus c plus ax2 over x2 plus c squared minus 2 times x2. The y partial derivative of g1 at x2, this term, becomes negative ax2 over x2 plus c. And this term simplifies a lot because x2, x equals x2, y equals x2, this is just 1. And this term, y equals x, also simplifies to just being negative b. And even though the Jacobian does simplify a little bit, we want to be kind of specific. And we'll look at a specific example for values of a and c, just to get some numbers down. So suppose a equals 3/4 and b equals 5 over 100. In which case then x2 will be 1 over 10 times 1 plus the square root of 6 and our a is just the matrix a11, b, a12, negative b. Where a11 is equal to 1 over 25 times 53 over 2 minus 17 square root of 3 over 2, which is approximately equal to 0.22717. And a12 is equal to 1/5 square root of 3 over 2 minus 9 over 2. And because this is a 2 by 2 matrix, we know how to classify the critical points. We look at the trace of A, which is this a11 minus b, the sum of the diagonal components of the matrix, and we look at the determinant of A, which is this times this minus this times this, which simplifies to 2 over 25 times 3 square root of 6 minus 2, which is approximately equal to 0.47. times b, which is greater than 0. And so the thing that really determines the stability of the system is b. Specifically, if a11 is less than b, this is going to be negative. A1 minus b will be negative, and therefore this equilibrium point will be asymptotically stable. Which means solutions close to it should converge into that point. Remember, this is specifically the point x2, x2. And if b is less than a11, this equilibrium point will be unstable. Because this will mean that the trace is positive. And we can actually, definitively analyze this using the plot from 4 very, very nicely. So this is the plot from 4, and if you consider the fact that in this region x prime is less than 0, and y prime is less than 0, in this region x prime is less than 0, and y prime is greater than 0. In this region, x prime is greater than 0, and y prime is greater than 0, and in this region, x prime is greater than 0, and y prime is less than 0, as well as in this region right here, x prime is greater than 0, y prime is greater than 0. In this region, y prime is less than 0, and x prime is greater than 0. And we can even look at these regions as well. This quadrant 1 inside quadrant 1 we have a region where the solution is positively invariant. Because if it's negative here, x prime is negative here, and y prime is negative here, solution direction will be like this. X prime is negative here, and y prime is positive right here. The solution direction will be like this. X prime is positive in this region, and y prime is positive in this region, so the solution direction will be like this. And lastly, x prime is positive in this region, y prime is negative in this region. So the solution direction will be like this. We can go through and construct a positively invariant region and directly show that this region surrounding this equilibrium point is in fact positively invariant. And what's incredible here is that by the Poincare Bendixson Theorem, we have that, well, if this is asymptotically stable, this critical point is asymptotically stable, there's no problem, because the solutions will go ahead and just converge to this equilibrium point. But in the case of it being unstable, we have that there has to be a limit cycle for this system of differential equations that describe the predator-prey equations. And this gives us exactly rigorous justification for why this is the case. So let's go through and look at the solutions. We'll look at the specific solution for B is equal to 0.3, which means that it's greater than A11. And sure enough, we see the solutions are all converging down onto that equilibrium point. So this is a very convincing justification of what we just did. And you see the solutions are slowly but surely spiraling down onto that equilibrium point. However, if we slightly change the value of B by just a little bit, so we move it down to 0.15, you see the bifurcation that occurs. And this is the old solution for 0.3. Give me 1 second to open up the solution for 0.15, and that's right here. The equilibrium point bifurcates and goes from being asymptotically stable to unstable, and thus we get by the Poincare Bendixson theorem the appearance of this limit cycle. So this is very, very incredible. And what's even more incredible in my mind is the fact that we can definitively understand this mathematically with what's going on here.